an astronomer. It is an astronomer?
Right.
Locally,
yes. Locally, we have both a technician and an astronomer. Right. And then what we have is like people who do half shifts. For instance, here in Europe, we start at 8 a.m. and we finish by lunchtime. So it's only the morning.
I spent 1 week there.
Right.
During commissioning. Wow. Before commissioning was a lot of fun.
That was the interesting time, probably. A lot of things happening.
Okay, so just you all know we are already live on YouTube. Do you mind if we wait 2 more minutes?
No, that's fine.
I think we might people again join us.
I will have to leave in an hour from now, but the seminar should be quite short. I think it should be like less than 40 minutes, maybe 35, 40 minutes. So I don't know, do you usually wait at the end for questions or do you have interruptions? I don't mind either way.
Usually we have the questions at the end.
At the end, so. Perfect. Yeah, so I think that, as I said, the seminar should be 35, 40 minutes, and then I'm happy to stay for questions for 15 minutes or so.
Okay. My microphone was a little low. Is it better now?
Perfect.
Okay. So. All right. I think we can start. Andreu, I'm gonna do a short introduction and then I will pass you the floor. Okay.
Perfect.
All right, so let's start. Hello, everyone, and welcome to another talk in our webinar series. Today, we have the pleasure of having Dr. Andreu Font-Ribera from the Universitat de Barcelona. He's a staff scientist at the Institut de Física de Altas Energias in Barcelona, working in the field of observational cosmology. Particularly with the analysis of large spectroscopic data sets to study the large-scale structures of the universe. And today he has joined us to talk about studies of the expansion of the universe with data from the Dark Energy Spectroscopic Instrument. Before we start, a quick reminder, this webinar is also being streamed live on YouTube, and you can find the link on our website or access it on our YouTube channel, LIneA MCTI. Andreu, thank you very much for being with us today. And the floor is yours.
Thank you very much. And thank you for the invitation to give this seminar. So let me see, I'm gonna try to share my screen and let's see if I can also share the sound that sometimes gives me troubles. Let's see. Okay, how do I share the sound now? How did we do that before, Rodrigo? I cannot find this.
You click in share screen and then you go in the bottom of
the
there. Screen,
okay.
You have share sound, okay?
Right. So let's see if I can do this now. So share screen, you should be. Oh, perfect. This will work now. Perfect. Okay. So share computer sound. Right, so I think this should work now. Perfect, thank you very much. And apologies for this brief interruption, technical issues. Right, so today I will be talking about the Dark Energy Spectroscopic Instrument, or DESI. It's using this telescope, the Mayal telescope that you can see in the background. And in particular, I will be talking about studying the expansion of the universe, but not using regular galaxies. I believe other people in this webinar series have already talked about this recently. I will be talking about using quasar spectra to study the expansion of the universe. So as a motivation for this talk, well, large-scale structure can be very useful for several things. For instance, we can use the distribution of matter in the universe as a function of scale and as a function of time to learn about the accelerated expansion of the universe. What is it that is causing it? Is it dark energy? Is it some modified gravity? Is it maybe a cosmological constant? We can also study the initial conditions of the universe and test models of inflation. we can learn about the physical properties of dark matter, whether if it's cold or warm or different other properties of dark matter models. And we can also measure the mass of the neutrino species because it also has an impact on the distribution of matter. So those are basically the main science goals that are behind these very large redshift surveys that have been popular the last couple of decades and that we continue to design and build for the future. So what is the main problem? As you know, we cannot always see dark matter directly, so we need something else. We need tracers that allow us to study this dark matter component, right? So by the way, sorry, in this talk in particular, we'll be focusing on the accelerated expansion of the universe, right? I will not have time to cover all these other topics, but I also saw that recently other speakers have been talking about some of these other topics. So what are these tracers that we use? Well, the most common one, the one that has been used for, I would say, 40 or 50 years, is to make maps of galaxies, right? We construct maps of galaxies with angular positions and redshifts to have to study this large scale distribution of mass through the number counts of galaxies. And for instance, here I'm showing a plot of slides across the universe of the galaxies from the BOSS survey, from the Sloan Digital Sky survey. I'll be talking about this survey later on. What I want to say with this plot, though, is that it gets harder and harder to go to high redshift because galaxies get fainter, and it's just not easy to have enough galaxies to study larger scale structure well enough if we want to go to study, say, redshifts above 2 when the universe was much younger, right? So if we want to study how the universe has been changing, we want to study the universe when it was young. And to do that, instead of using galaxies, we can also use other types of tracers. And for instance, in the BOSS survey and in DESI, we also used another technique called the Lamin alpha forest. So in this talk, I will be talking mostly about these fluctuations, these maps that we can get from this new technique called the Lamin alpha forest, that basically we are mapping the neutral hydrogen in the universe. So these blue and red fluctuations are regions of the universe that have more or less neutral hydrogen compared to the mean density of hydrogen. And this gas is absorbing some of the photons that we get from these very distant quasars. I'm going to be talking about this in more detail in a while. So the outline of the presentation is I'm going to start by an introduction, by giving us a brief introduction on what are these baryonic acoustic oscillations that are one of the key components of these surveys. These baryonic acoustic oscillations, we refer to them as BAO, right? And I'm going to be presenting results from some of these earlier surveys that were targeting BAO as their key science, in particular BOSS and eBOSS, that were done during the last decade. And in particular, I will explain why we want to go to high redshift and measure BAO, not only with galaxies, but also with this Lamin alpha forest technique that I mentioned. In the second part of the talk, I'm going to talk about the cosmological interpretations of some of these BAO results. I saw that recently Héctor Gilmarín has already presented some of these results. I think it was a month ago. And Kyle Dawson, who was one of the PIs of eBOSS, mentioned that he's going to be talking about this also in a couple of months. So I decided to make this section a little bit shorter, and I'm going to spend more time on the feature of BAO, and that is the Dark Energy Spectroscopic Instrument, or DESI. And I will give an overview of the survey and the instrument, and finally show some early measurements that we have already obtained from this survey. So let's get started. Right, so why do we want to do these BAO studies? Is because if we can, in general, astronomers, right? Astronomers usually want to know how far galaxies are, because we might want to know how bright they are. And in order to know the intrinsic brightness, we need to know how far these objects are so that we can correct for the flags, right? In general, most astronomers say, well, if I have a model of the expansion that my friends cosmologists gave me, I can compute how far a galaxy is given its redshift, right? But that's not quite what we want to do, the cosmologists, right? We cosmologists want to do the opposite. We would like to know what is the distance to many different galaxies for which I have redshifts, such that I can learn about what is the Hubble expansion, what is the model that causes this expansion of the universe. So if we could have multiple measurements of distances at different redshift, we would be able to understand the expansion of the universe much more accurately. For instance, because radiation, dark energy, matter, curvature, and so on, they all have a different dependence, their density have a different dependence with redshift, we would be able to reconstruct how much matter, how much radiation, how much dark energy, and so on is there in the universe by measuring these distances to different redshifts, right? So we can learn about dark energy if we can measure distances. This is one of the key points that is driving all these efforts to measure BAO. It's also one of the key points for the supernovae surveys, right? Supernovae are very efficient ways of getting distances to different redshifts. Because we know how bright one of these supernovae is, by measuring its apparent flux, we can infer what is the distance to those supernovae. The technique is called standard candles, and supernovae are one of the best examples for how to use these standard candles to measure distances to different redshifts. Then the second technique is the standard rulers. If we knew how large a given object is in physical units, and we could measure, for instance, its angular size in the sky, we would also be able to know how far it was, right? So that technique called the standard ruler is also very useful. And in particular, the BAO is one of the best standard rulers that we have. And I'm going to be explaining it in a couple of minutes with a little bit more detail. Recently, in the last 5 years or so, there has been a third way to measure cosmological distances, not using a candle, not using a ruler, but what it's called standard sirens. And that means that if we know how loud an event, for instance, a gravitational wave event is, we can also infer how far those two neutron stars that were merging, how far they were. And if we have an optical counterpart that gives us its redshift, then we can also constrain cosmology by looking at this diagram. You can call it a Hubble diagram of binary neutron stars. So once we have this, once we have a motivation for why we want a standard ruler, we want a standard ruler to measure distances, and we want to measure distances to learn about the expansion of the universe, right? So where can we get a standard ruler? So maybe 20 years ago, it was proposed to use these baryonic acoustic oscillations as a standard ruler. These oscillations are a phenomenon that happens in the very early universe, above redshift 1000, when photons and baryons, basically protons and electrons, were very tightly coupled, and there were pressure waves that were traveling across the universe. And these waves, these waves traveled until the universe recombined, in the sense that protons were able to capture electrons and form hydrogen atoms. And at that point, the radiation stopped interacting as strongly as it used to do with the rest of the plasma, and these acoustic waves basically froze. They stopped traveling, and that left an imprint in the distribution of matter. So here's an animation by Daniel Eisenstein that shows an initial overdensity in the universe that is causing an expansion, a wave to propagate from this outwards. But when recombination, right, the universe gets neutral and that wave stops, and it leaves this imprint at a fixed scale that we call the sound horizon at recombination. So if we know the sound horizon at recombination, and we actually can compute it quite accurately thanks to CMB experiments like Planck. So if we know what is the size of these acoustic waves, and we can see this imprint in the distribution of galaxies in the universe, we will be able to use this as a standard ruler. You'll see it more clearly in a couple of slides. So these oscillations are nothing really new. We have seen them in the CMB, in the temperature power spectrum of the CMB, for maybe 20 years now. You can see here the latest results from Planck. These peaks, these up and down features, these oscillatory features here, are related to these acoustic oscillations that I was mentioning. And as you can see, we measure very accurately what is the angular scale here from the CMB. But not only that, using the peak heights, the different heights of the different peaks, we can also learn about the density of baryons and the density of matter in the early universe that basically set what is the size of this sound horizon that I mentioned about. So these same features, did I stop sharing? No, wait, there you go. Can you see it well now?
Yes,
sorry, I don't know what happened. So these features that we see in the CMB temperature power spectrum, we also see them in galaxies. And if we can measure a peak in the transverse correlation function, so the correlation function of galaxies as a function of angular separation, so let's call this delta theta. And if we can measure these also along the line of sight, so redshift differences, correlation function as a function of redshift difference of galaxies, let's call this delta V. From those two measurements, since we know the physical length of the ruler, this RD, the sun horizon at the Dirac epoch, we will be able to measure both at the same time the angular diameter distance to that redshift, but also the Hubble parameter at that redshift. So we will learn about the expansion of the universe by measuring these BAO measurements and treating them as standard rulers. So this was one of the main motivations of the Baryonic Oscillation Spectroscopic Survey, or BOSS, and its extension eBOSS. So already in SDSS, so SDSS was the Sloan Digital Sky Survey, right? It started in the late 90s and it ran basically for 2 decades. During the first decade, what it's known as SDSS 1 or 2, it already measured BAO for the first time. But it was the second, so it was the BOSS survey started in 2009 that really made a very, very precise measurement of BAO, because the whole survey was designed basically to measure BAO from galaxies very accurately. Right, so this telescope was not particularly large. It's a 2.5 meter telescope in New Mexico, but it has a very large field of view that allows us to map the sky very efficiently. So we cover 1/4 of the sky in 5 years. And at every pointing, we obtain spectra of 1,000 galaxies or quasars in one pointing. So it was very efficient at mapping the largest scale structure of the universe with galaxies. So the final data set was released in 2019 and it's public. So everyone is welcome to play around with these beautiful maps of galaxies. And here I'm going to show something from the press release that we had in SDSS last year. I think it was last summer. And you can see here the different colors indicate different types of galaxies that we have studied to study the universe. And you can see near the center, we are sitting at the center of this sphere. Near the center, in green, those are measurements from the bright galaxy surveys from SDSS 1 and 2. Then as you go to outer redshift, to larger redshifts, you go to the red galaxies or LRGs from BOSS. Then you also go to the emission line galaxies in blue. Those will have a very important role in DESI. You also have the quasars in yellow. And if you go to white, you have these measurements of the Lyman alpha forest. And for each of these different types of galaxy data sets, we measure here on the right, you can see these features are the BAO peaks, this detection of extra correlations at a particular scale that we use to then as a standard ruler. So these different peaks that we measured from SDSS, you can also see them in this different diagram, where we plot here is the distance that we infer from these BAO distances divided by the prediction from a Planck model, from a flat lambda CDM model inspired by the best fit results of Planck. So you can see that overall, there's a very good agreement between the BAO measurements from SDSS and the predictions from a flat lambda CDM model with the best fit parameters from Planck. And you can see that we cover a fairly wide range of redshifts. On the best measurement is around redshift 0.5 or so from the BOSS LRG galaxies. But also at redshift 2, above redshift 2, we have a 1.4% measurement of BAO using the Lyman alpha forest. So why do we want to go to high redshift to study the Lyman alpha forest? I'm going to try to motivate this with a couple of slides. So you've probably seen this diagram many, many times, saying that 70% of the universe is made out of dark energy, and we don't know why, what is causing this, what is this dark energy. But this diagram is made at redshift 0. This is the composition of different components at redshift 0. If we go to high redshift instead, what you will see is that as you go to high redshift, there's less and less dark energy. And by the time you are around redshift 2, pretty much all the universe is just matter. right? So by studying the expansion above redshift 2, you're basically qualitatively looking at a different universe, where dark energy is just a residual component of the energy content in the universe. So I think by itself, that's already a good justification for why we want to go to much higher redshift. A more quantitative way of explaining why this is interesting and why it helps our cosmological constraints is by doing this toy exercise. I'm gonna show you a toy model that, and I hope it's useful to understand how it helps in cosmological constraints. So imagine a universe that we know it's flat and it's a lambda CDM universe, and let's assume that we also know with infinite precision the sun horizon, the scale of sun horizon RD, right? In a flat lambda CDM universe at low redshift, there are just two free parameters. There's H naught, the current expansion of the universe, and there's omega m. And there's nothing else because omega lambda is just 1 minus omega m, right? So both the line of sight distance, H of Z, and the transverse distance, dA of Z, they're both led by these two parameters. So now let's assume that we have BAO measurements at two very different redshifts. They're both 2% measurements along the line of sight and in the transverse direction. And let's see what happens. So at redshift 0, H of Z is basically H naught. That's the definition of H naught, right? So, and also dA, because the integral is so short, you're integrating between redshift 0 and redshift almost 0, you're just also measuring H naught, right? So you can see here what are your constraints. In blue is from the line of sight measurement, and in orange is from the transverse measurement, and green is the combined. And you can see that from both measurements, all you're doing is measuring H naught, or H is H naught divided by 100, right? You can see that you have no sensitivity to the matter density of the universe, omega m H squared. Now, if we go to high redshift, the picture is going to change a lot, because H of Z now, the term that has omega m in front, will dominate. So H of Z basically will measure H naught times square root of omega m, or in other words, omega m H squared, right? So the line of sight measurement in blue, now it's completely horizontal, or almost horizontal, right? Because it's directly giving you omega m H squared. While the orange one, that is the transverse, now it's an integral that changes quite a lot between redshift 0 and redshift 3.4 in this case. So it's somewhere in between. It's this diagonal in orange, right? And by combining both, now the green measurement, it's actually giving you a closed contour around, and by combining orange and blue, right? So you can see here in a more quantitative way why looking at high redshift gives you a different picture of the universe. It's allowing you to constrain parameters that at low redshift alone, BAO cannot constrain. So we can also look at this at different redshifts by running this GIF that shows, I don't know, I like making GIFs, and I thought this was quite useful. So you see, as the redshift goes up and up and up and up, the line of sight measurement in blue just keeps tilting, and above redshift 2 or so, it's pretty much horizontal. Right, so how do we go to high redshift? So in the BOSS survey, in the eBOSS surveys, and in the DESI survey, we went to high redshift to study BAO by using this phenomenon known as the Lamin alpha forest. And what is this? As I mentioned in the very beginning of this talk, the Lamin alpha forest is a series of absorption features in the spectra of high redshift quasars. So I'm showing in this plot two optical spectra of quasars. The one on top is at a low redshift quasar, it's redshift 0.16, and the bottom one is a high redshift quasar at redshift 3.62. You can see that they look quite similar because I have shifted both, well, not me, the author of this figure, William Kill, has shifted both to emitted wavelength, right? So they look very similar. They both have a fairly flat continuum with a very clear and white emission line at 1200 angstroms. This is the Lamin alpha emission line, right? But the key difference is that to the left of that line, once you go to high redshift quasars, you see a huge amount of absorption lines. And those absorption lines, already in the 70s, people realized that this was neutral hydrogen along the line of sight between the quasar and us. And every time that the photons from this quasar were traveling towards us, like they were being redshifted as they traveled. So every time they found a different amount of gas of neutral hydrogen, because the light had been redshifted since it left the quasar, it's now absorbed at different wavelengths. So what we see here is information over many, many different redshifts. For instance, this particular quasar, we usually define, well, in general, in this analysis that we're going to be talking about, we usually define the Lyman alpha forest region as this region between the Lyman alpha emission that I talked about and the Lyman beta emission. That's this milder peak that you see on the left of the spectrum. To the left of that, things get a little bit more complicated because there's also Lyman beta absorption. But in this region that is a little bit cleaner, we call this the Lyman alpha forest. And for instance, for this quasar at redshift 3.6, we can use that line of sight. We can use that spectrum to learn about the line of sight density all the way between redshift 3 to redshift 3.5. So from every quasar, we roughly get like a delta redshift of 0.5 or so of information. So we understand fairly well how these things work. We have very detailed hydrodynamical simulations that explain very well most of the statistical properties of these absorption features. Here I'm showing a simulation by Andreu Font-Ribera, and it shows the quasar continuum as it started with no absorption. And as it travels across the universe, it's being redshifted. The light is going to the right? But also every time it finds a different amount of cloud, you can see absorption that always happens at the same wavelength of 1200 angstroms, plus some residual absorptions that happens at lower wavelengths. Those are Lyman beta, Lyman gamma, and other higher energy absorptions. That's why we usually only work with this limited range of absorption that is a little bit cleaner. So how do we do this analysis? So we take this spectra of high redshift quasars. This one in particular is from BOSS. It's one of our nicest spectra. They will not look that beautiful in the sense that BOSS was not targeting particularly bright quasars. So we have some brighter, some fainter, but statistically we can still use all of them to measure these baryonic acoustic oscillation features. So what do we do with the spectra is we take the spectra of the quasar and we have to do something called continuum fitting, that is basically guessing what would have been the level of flux if there was no absorption, because we are interested in quantifying what fraction of the flux was absorbed. That's what we call the transmitted flux fraction that I paint in green in the equation in the right. So there are different ways of doing continuum fitting. We can talk about this at length later if you have questions, but they're not that important for BAO. It's actually fairly easy to do a continuum fitting that allows you to measure BAO well enough. So once you have this transmitted flux fraction, or capital F, what we're interested in is to measure fluctuations around the universe of this quantity. So we need to measure the mean flux, right? This F bar, and we compute this delta F, these fluctuations above and below this mean level of absorption. That of course changes with redshift, but we have then these delta Fs that we basically treat at this point as any other tracer of the universe. We can measure the correlation function, the power spectrum, the bispectrum, anything you want, right? In particular, to measure, right, let me clarify something here though. Because we have defined delta F in this way, regions of the universe that are denser will have more absorption, right? But that means they will have less transmitted flux. So high density means low F, and it means negative delta F. So we will see later on that the Lyman alpha forest defined this way is a negatively biased tracer. So it have a bias that is smaller than 0. And this may be confusing sometimes. So how do we use this delta F, these fluctuations in the Lyman alpha forest? One of the things we do is we measure the autocorrelation of these fluctuations from 2 different skewers, right? From 2 different lines of sight to 2 different quasars. In BOSS, sorry, at the end of eBOSS, we have around 220,000 of these quasars. So we had many information from multiple lines of sight. And what we were looking is at coherent absorption from neighboring lines of sight so that we could cross-correlate to measure this correlation function and get this extra peak in the correlation function that is the BAO peak, right? We also looked at another technique that is called the quasar Lyman alpha cross correlation, and that is correlating this delta flux, these fluctuations in the flux of Lyman alpha with the density of quasars themselves, because quasars are also tracers of the density field. So they both trace the dark matter density and they are correlated. And we were also able to measure BAO in this cross correlation. So I'm going to show you now results from the final results, sorry, the final data set of EBOS. This paper appeared last year. It was led by Léon Dumas de Bourboux. And you can see here different plots of the correlation function of this gas, the autocorrelation function of Lyman alpha 4 that I was talking about. And you can see that, so those different panels are basically plots for different orientations. So top left is line of sight correlations, while bottom right are transverse correlations. So 2 pixels that are the same redshift but at different angular positions. And these plots are as a function of of separation R, right? And you can see that in all these panels at 100 megaparsecs divided by h, this is a clear feature that corresponds to this BEO peak. And this is the detection of where is this peak localized that we were able to measure at 1.5% precision and use that to learn about cosmology. As I mentioned, we were also able to do this in the cross correlation of quasars on Lyman alpha forest. And this is what I'm showing here. Again, top left is line of sight correlations, bottom right are transverse correlations or perpendicular. And you can see that in all of them, you can also see this peak at around 100 megaparsecs, but now the peak has been flipped, right? It doesn't look like a peak, it goes like a dip. And the reason for that is because remember I mentioned that the Lyman alpha forest is a negative tracer. So the quasars are positive tracer, and the product of the two of them makes the correlation function to look like it has been multiplied by -1. But it doesn't matter. We can still fit the position of this peak very accurately. So in EBOS, as I mentioned, we were able to measure this BEO peak along the line of sight, and that's what we called alpha parallel, is the ratio of this line of sight distance divided by our fiducial model. And in green, I'm highlighting the transverse BEO measurement that gives you the angular diameter distance at the redshift. And we were able to measure both so if you look at the bottom left panel, I'm showing the result from the autocorrelation of the Lyman alpha forest in blue, the cross correlation in black. They are very consistent one with each other. And when we combine them, we get the red contours that are the combined results from EBOS DR16. And in the bottom right, sorry, in the right panel, I'm just showing the results, how they have been evolving since the results from BOS DR12 to EBOS DR16. The error bars have been shrinking a little bit, and the best fit values have shifted a little bit towards 1 here means the predictions from Planck. So they are now at like 1.5 sigma away from Planck, but still fairly consistent. Right, so as I mentioned, we can learn about cosmology from these BEO measurements. We had a paper that is EBOS collaboration et al. 2021. But since, as I mentioned, like other speakers have talked about this, or will talk about this soon, I decided to make this section shorter. I will only talk about one of the things that I was more interested in this paper is the section on the Hubble tension. So you have probably heard about this Hubble tension because it has been quite a popular topic for a few years now. And the tension is that we don't quite know how fast is the universe expanding now. Right? This is the value of this H0 parameter. And if we look at distant ladder measurements using Cepheids or other techniques, they seem to indicate a value of H0 that is around 73. But on the other hand, if we use cosmological measurements, for instance, from the CMB, it looks like H0 is significantly lower, around 67. And the tension now could be probably something like 4.5 sigma or something like this. Enough for us to pay attention to this. So this is one biased way of explaining the different measurements that we have. As you can imagine, I worked at the SDSS collaboration, so there are a lot of points here that say SDSS, but I think it's still a very valid point that there are some collaborations, some results that prefer a high value of H0. The two most important ones probably are these shoes measurements using Cepheids for the distance ladder. Also, Holy Cow, that is a strong lensing measurements of H0. Some of them are in between, like SPT or TRGB or the LIGO gravitational waves. And then pretty much all the cosmological analysis, doesn't matter how you combine them, they all prefer low values of H0. So it's not limited to Planck. We can use WMAP instead of Planck, or SPT plus SDSS, or ACT plus SDSS. They all prefer clearly low values of H0, right? However, it is true that most of them assume a flat lambda CDM model. So maybe the problem is with the model, right? And it is also true that most of them assume that the universe, assume the value of the sun horizon. So maybe the problem is with the sun horizon. So we're gonna look at this, right? And I'm gonna be showing that actually we can get still measurements of H0 that are low, even if you break each of those two assumptions one at a time. So how come? So BAO, as I was talking, remember in the toy model that I was mentioning, we are sensitive to both H0 and omega m, right? Within a flat lambda CDM universe. So in this particular slide, what I'm talking about is, let's still assume that the universe is flat and lambda CDM, but let's not use CMB at all, right? Let's forget about Planck, let's forget about any other CMB experiment, and let's see what is the value of H0 that we get from BAO with assistance from Big Bang nucleosynthesis. And why we need Big Bang nucleosynthesis is because BAO alone cannot measure the density of baryons, and the density of baryons is important to calculate the sun horizon RD that I was mentioning before. Otherwise, BAO alone it's completely degenerate sun horizon and H0. So what I show here is that by using low redshift BAO with Big Bang nucleosynthesis, we get these diagonal contours in red, right? Those are from the galaxies of SDSS. And then by adding the quasars and the Lyman alpha forest that I presented later on, the degeneracy in gray is a lot different, right? This comes back to this toy model that I explained earlier in the talk. And you can see that by combining both, now we have a very good measurement of both omega m and H0, and they are perfectly consistent with Planck, right? Omega matter around 0.3 and H0 around 67 or 68. Again, this measurement does not use CMB, and still highlights that the tension with the distance ladder, that here is this horizontal gray line, is still very much present. It also highlights the importance of adding the Lyman alpha points at high redshift, because otherwise, with just the galaxies in red, it would not have been very easy to tell apart one measurement from the other. Another thing we can do is what we call the inverse distance ladder. And it's a little bit complicated, but I still think probably I still have time. So what we do is, instead of building a normal ladder, a normal distance ladder that we start with like parallaxes to calibrate Cepheids, to calibrate supernovae, and then we use this to measure H0, that's the normal distance ladder, we can do the inverse. If someone tells us what is the sun horizon, the size of the standard ruler, we can use BAO to get really good distances to redshift, say 0.5, right? Thanks to the BAO from SDSS. And then we can calibrate the supernovae with this BAO, and then look at what is the distance and what is the expansion at redshift 0 using these supernovae that now have been calibrated thanks to the BAO and the sun horizon. So it's like we're building the ladder to the supernovae, but starting from high redshift instead of starting from low redshift, right? So these are the results in pink. And what I'm showing here is that when we do the inverse distance ladder, we don't need to assume flat lambda CDM. We can allow the universe to have an open curvature, to be open or curved, different curvatures. We also don't need to impose lambda. We can have dark energy that changes with time. And even then, because supernovae and BAO combined constrain this so well, we are still very inconsistent with the distance ladder, right? So the results here in pink, that are the inverse distance ladder that I mentioned, in combining CMB, BAO, and supernovae, we are still in strong tension with the distance ladder, even though now we are not imposing a flat lambda CDM model, right? So going back to this comparison, I think it's clear that it's not a problem with the CMB. And I think it's also clear it's not a problem with flat lambda CDM. It's something else, right? So my take is that if there is no systematic hidden in somewhere else, it has to be something about the physics of the early universe that we just don't understand, right? Because all the measurements on the left assume that we know the physics that set the sun horizon scale RD. If that is not true, if we are somehow missing a key ingredient, all the measurements in the left would have made the same mistake, and that could also explain the tension. But unfortunately, many smart scientists have spent many years now trying to find ways of doing that, and it's just not very easy to find a model that could do this. Right, so I'm going to use the last few minutes of my talk to talk about DESI, the next video survey that has started already, and we are all very excited to see preliminary results. And after giving many talks about DESI, I realized that the best way is to use a video that was already generated by DESI. It's only 1 minute, so please, I hope it's not too much. But I think it does a very good job at describing the instrument. So I'm going to play it.
Light first reflects off of the telescope's 15-ton primary mirror, then onto its 6 large lenses that ensure DESI maintains a wide, highly focused view of the sky, covering an area about 38 times larger than the full moon. These lenses are housed in a device that can be adjusted within millionths of a meter to preserve the alignment of those lenses. After passing through the set of lenses, the galaxy's light reaches fiber optic cables in DESI's focal plane at the top end of the telescope. 5,000 robotic positioners, each carrying a single optical fiber, are programmed to move to pre-selected sequences of galaxy targets. This automated dance of robots allows DESI to target sequences of thousands of galaxies at a time. The optical fibers, which serve as DESI's eyes, send the galaxy's light down the length of the telescope to 10 spectrographs.
Right. So in case this was not too clear, I also have a backup way of explaining it. But as the video was saying, this telescope, I guess the key thing, apart from the telescope being larger than SDSS, now it's 4 meters instead of 2.5. We have constructed this DESI instrument that has 5,000 fiber positioners that move robotically and that allow us to constantly, like every 15 minutes, we look at a different part of the sky, we change the position of all the fibers, and we take 5,000 new spectra, and it allows us to increase the speed of the survey by a lot. And one of the key ingredients was this optical corrector that you saw in the video. You can see it also here at UCL, where I was until recently. It's huge, and it's incredible that it's super heavy, like something like 2 tons, and it's still able, like the telescope is still able to move around with this sitting on top, and it works just great. So here you can see the real telescope with the corrector on top and ready to move. That was in 2018, early 2019, when commissioning started. A few more pictures of the instrument. On the top left, you see the focal plane. It's a little bit more, you can see the hand of a human next to it, so you can guess that it's like 1 meter and a bit. And it is split into 10 petals. So there are these 10 pizza slices, right? And each of them are basically independent instruments, right? So each of them has 500 fiber positioners. You can see them in the top right figure. This is one of the petals with the 500 fiber positioners, sorry. And each of them go to a different spectrograph. So we have 10 spectrographs. And each spectrograph has 3 cameras that you can see at the bottom left. So there's the red arm, the blue arm, and basically the infrared arm. So, although it's very near infrared, it's not really infrared. And you can also see in this new picture of the focal plane at the top left that every petal also has these small squares at the edges, right? You can see them in blue and orange. Those are what we call the GFAS, the guiding and focusing alignment camera. And that's what allows the telescope to continuously be in the right position for observations. And these cameras were built at IFAE here in Barcelona. So what's the plan for DESI? During the next 5 years, DESI will take the spectra of something like 50 million objects, most of them galaxies, but also stars. So there's a Milky Way survey that you can see at the bottom of this table, right? When the moon is up, for instance, tonight it's almost full moon. I think it's tomorrow, full moon. We will not be looking at quasars. The sky is just too bright. So we will using the time around the full moon to look for bright galaxy surveys at low redshift. You can see that at the bottom part of the table, and to look for Milky Way stars. We'll get roughly 25 millions of these objects between stars and bright galaxy surveys. But the most interesting thing for dark energy is that during the dark time, when the moon is not so bright, we'll be looking at LRGs below redshift 1. We'll be looking at emission line galaxies up to redshift 1.5 or so, and we'll have 17 million of those. And then to go to higher redshift, we'll use the quasars. We'll have 2.5 million of those, including the Lyman alpha quasars that above redshift 2.1. So the goal is to take these current measurements. Actually, this plot is a little bit outdated. I wanted to update it for this talk, but I didn't find the time. Apologies. So this is from a couple of years ago. But these are the current measurements of the expansion rate of the universe using BAO from different surveys. And this is how it will look with DESI. We'll have many, many new points with explicit error bars that will allow us to track down the expansion of the universe with very high precision. And just to finish, I want to show, I think it's 3 slides from early results, early measurements from DESI. So survey validation was about to start in March 2020. I was actually at the telescope in Arizona when COVID not started, but basically exploded in Arizona and in Europe. And we basically had to shut down the telescope for many months. So we restarted in December 2020, and it lasted 4 or 5 months. So in early May 2021, we finished what is called the survey validation phase of DESI. And even though it was only a few months, we already collected more than 1 million redshifts. And you can see here in these different histograms for the bright galaxy surveys, the LRGs, the luminous red galaxies, emission line galaxies, and quasars, that they cover different redshift range. And we're going to have a lot of these objects. And this first million redshift that will be released with SV, this will be publicly available somewhere in mid-2022. So even if you're not in DESI, you will be able to start playing with these catalogs very soon. So apart from SV, we finished in May and we started the main survey. Sorry, but before that, already from SV, we can already measure these correlations of the Lyman alpha forest that I was mentioning before. So here I'm plotting the correlation function in a slightly different way. They're color-coded and then shown as a function of R parallel, so line of sight separation, and transverse separation or angular separation. And on the left panel shows the measurement from DESI SV, and the right shows the panel of EBOS, actually the combination of BOS and EBOS, so 10 years of observation from SDSS. And you can see that they're in very good agreement, and even though the measurement from DESI is still noisier, very soon it will be better than the combination of BOS and EBOS. We also measured already the cross correlation with quasars. It also looks great. Very good agreement with EBOS, so nothing strange in the data. And the final slide is that the survey has been a lot of good progress. We have already covered 10% of the full DESI survey during these 4 months since survey validation. The main survey already has almost 5 million redshift, including survey validation. We are above 5 million redshifts. And you can see here the footprint that we will cover. There's a North Galactic Cap that is larger and a South Galactic Cap that is smaller. Blue means that we have covered that area with 1 pass. Orange and green means 2 and 3 passes and so on. And you can see that this is going really, really fast, actually above the expected so far. So we will finish the survey sooner than expected if everything keeps going at this pace, fingers crossed. And that's it. So just to finalize, I hope I have convinced you that BAO is one of our best shots at measure the nature of dark energy, at understanding the nature of dark energy. The BOS and EBOS already made really good measurements of BAO, both at low redshift using galaxies, but also at high redshift using quasars and the Lyman alpha forest. And that DESI will do a 10 times better data set that will allow us to increase the precision by a lot. And it's not only BAO, as I mentioned, so it's not only dark energy. As I mentioned on my first slide, the same data set can be used to study neutrino masses, to study inflationary models, dark matter models, and many more. So that's it. Thank you very much for your attention. And I'll be happy to answer questions for 10 or 15 minutes or so.
Thank you, Andreu. Thank you very much for the remarkable, interesting talk. We now have a good time for questions from the audience. If you joined us on YouTube, you can put your question in the comment section and I will redirect it to Andreu. If you joined us here on Zoom, please raise your hand and ask your question. So questions?
Well, I just want to congratulate you. Beautiful talk, excellent. And it's really remarkable what DESI is doing and what it promised to deliver. Very nice project. Congratulations.
Thank you very much.
Okay. More questions? Andrew, I have a very basic question. You showed that the evolution of dark matter over dark energy over time. Where are we heading at? Is it in the sense how do you interpret this evolution? Like it's
Right.
coming from matter.
So far, so far, all cosmological data we have pretty much points into the same direction, that the density of lambda or dark energy is constant with time. And I think this is the simplest, but also the most boring possible answer, that everything seems to be in agreement with the cosmological constant. There's still room for different models of quintessence or models that predict that dark energy is dynamical or that we will be changing with time. But as the more data we have, the less room is there for these models. So I think after DESI, probably it's either we find something or there's not much more to be found in terms of dark energy. As I mentioned, there's a lot of other science that can be done with these galaxy surveys, but DESI will measure so well the equation of state of dark energy that there will not be a lot of room for deviations from lambda CDM.
Okay, thanks. And also another question: what is the resolution of the spectra that are taken with DESI?
Right, I didn't spend much time on
also
this.
Stars and
Right, I should have spent more time on this, but let's see. Do I have it here? No, I thought I had it here. Well, so basically SDSS had a 2000 resolution of 2000. So lambda over delta lambda, roughly 2000, right? SDSS. DESI will be a little bit better than this. It will be 3000 on the blue end of the spectrograph, something like 4000 or even 5000 on the red side of the spectrograph. So it will be a little bit better than SDSS, but still far from high resolution spectrographs that you might want to use for some stellar studies.
Okay, I saw that in the footprint that you also go very in the ecliptic. Is there any proposal or any idea of studying solar system objects, given that you have spectra in the near infrared region? To study this,
I think so. When I said infrared, probably I should have said extreme red, but not quite.
Okay.
You know, like it's really not infrared. Like we stop at 10,000 angstroms.
Okay.
Would that be enough to look at this type of objects? I'm not sure. Might not be enough, but no, I don't think there's a proposal. So we have allocated time for like secondary programs. So within DESI, people can submit projects that are independent to the main science of DESI, and you can either get some fibers every night that you can use for your targets, or sometimes for specific cases, you can basically get the telescope a few hours to do your own science. But this was especially the case during SV, during survey validation. During the main survey, it will be difficult to move the whole telescope to do something different, except we are also trying to do follow-up of transients. So for instance, if there are events of gravitational waves or events of ice cube neutrinos or things like that, sometimes the telescope does follow them. But I'm not sure about objects in the solar system, honestly.
Okay, just more curiosity. Okay.
Right. Also, one of the key things of DESI is that it has 5,000 fibers, right? So I'm not sure if you would have 5,000 targets to look at.
Well, in the near future, probably.
Maybe.
Yeah.
Right.
Well, maybe not.
Maybe after SST.
Yeah, it depends on the size of the object. Then.
Yeah.
To have a lot of them, you have to focus on the small objects, and then they will be really faint. Well, okay, thanks. So we still have a little time for questions. More questions? Okay. If there are no more questions, we'll now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Francisco Foster from the Universitat de Chile, continuing in our series on LSST brokers, talking about the Alert Chip project. Thank you everyone for attending, and a special thanks for Andreu.
Thank you. Bye everyone.
Okay, everyone have a great day, stay safe, and I hope to see you all next week. Bye-bye.